Hello everyone. Welcome to the week two. Let me just share my screen. Window. Yeah. Can you see my screen? The week two. This one.
Yes, we can see it.
Chalo, great.
Yes, sir.
Good. All right. Welcome to the week two live session for your course Introduction to Machine Learning. Um, my name is Raj Vijayan. I'm a PhD student in IISc and I'm a PMRFTA. Today's agenda is we'll do one probability problem just to drive home the point of some of the things that we have been learning in probability as such, and we'll see how to do linear regression using the Numpy library. And I'm assuming you had intro to Numpy library by on Tuesday session, right? You guys had it right on. Okay, good, fine.
Yes.
Yeah. Mm, Let me just open the chat here. Okay, good enough. Okay, and as usual, the what will be written here will be made available to you in PDF format, and the session is recorded. And my sessions will always be from 4 to 5 p.m. on Saturdays. And as usual, so I can't see the chat as such, so feel free to interrupt and ask any doubts you have. So last time we had some issues regarding the recording and stuff like that. So currently what I have made is I've made that you can join the Google Meet automatically. You don't have to wait for me to approve your joining in, and I'm also live streaming to YouTube right now, so if so hopefully we should not have any recording issues as such. But the max is still at 100 people, and we'll see how we can solve it, and in case we need to solve it. All right. Okay. So with that, we'll move to the first thing. So last time I realized I mentioned something called as total probability formula, but I think some people might not be very clearly aware of what is that and why do we even have such a formula separately and stuff like that. So we'll take 5 minutes to understand why the formula arose and what is the meaning of it and stuff like that. Okay. So I'll take an example, and I mean I'll show it in the graphical format first, and then we'll see how we arrive at that. All right. So let's say this is my whole sample space, right? S, and I'm dividing it into two events, B1 and B2. And I have another event which spans both the B1 and B2 space. Okay. So B1 and B2 are special in the sense if I union them, I get the sample space, and there is nothing intersecting them. So there is zero intersection between them, right? So whenever any two or more events satisfy such a condition, it's called a partition. So B1 and B2 are set to partition the space. Okay, partition S. All right. So now the thing is, so there is some intersection of A and B1, and there's some intersection of A and B2 also, right? So I can write the event A as A intersection B1, right? Union A intersection B2. All right. And the fact is that these two sub events that we have, these two intersections, these are also don't have anything in common, right? Okay, these two are also mutually exclusive. So if I had to write probability of A, we know that any event which is a union of two events, right, and such that your intersection is null among them, I can just write them as probability of A intersection B1 plus probability of A intersection B2, right? Because the third term, the minus term of the intersection is zero here, right? So now what I do is I can so now I can apply the conditional probability formula, right? So now, because what is probability of A B, I can just write it as probability of A given B into probability of B, right? So this becomes probability of A given B1 into probability of B1, A given B2 into probability of B2, right? This is the total probability formula. That's it. Simple. And the thing is, this can be extended to multiple events also, right? I mean, multiple partitions. So let's say I have n such events, okay, bi, where I goes from 1 to n, such that intersection among any of these two is phi, and union of all of them, right? So union of, so b1 union b2 union and so on, bn is the sample space. All right, if this is the case, I can still, if this is the case, then I can break it down in this format. So I can just write it as summation I equal to 1 to n probability of A given bi into probability of bi. All right, and see, since all the union of all these events, union of all these events is the sample space, and none of them are intersecting with each other, so I can write summation of I equal to 1 to n probability of bi also as equal to 1, right? Right. So if you apply the union formula for probability of this particular union set, you will and since each of them is mutually exclusive, you will get this answer, you will get this, right? So this is basically expressing probability of A as a weighted sum of these probabilities, right? So these are the weights, and this is what you're summing over, right? This is like taking the average of this probability of A given bi, but with some weights, and the weights are given by probability of bi. Okay. So any doubts until now?
Hi, Raj.
Yeah, tell me.
Yeah, I had a doubt this time. Just a clarification. So, can it be extended to denumerably infinite sets for this conditional probability?
Yes, that can be done. So we have, so there's something called as countable union, uh, you know, s- uh, s- setting, where, so if I have bi going from I equal to 1 to infinity, and these form a partition of S, right? So then I can still apply this particular thing, right? Because what happens is, so in that case, what happens is this particular, setting, you take a sum of countable unions of these, um, uh, countable union of these particular condition probabilities. So this can be extended to infinity also. Yeah.
Thanks.
Yeah. Any other doubts? No? Okay. Okay, so we'll go to the first problem of the day. So this is one problem that I found a bit interesting when working on probability. So let's say we have a question here. So we say that there's an urn which contains 4 white and 4 black balls, and we randomly choose 4 balls, right? If 2 of them are white and 2 are black, then we stop. All right. If not, then we replace the balls in the urn and again randomly select 4 balls. All right. Then so this continues until exactly 2 of the 4 chosen are white. So what is the probability that we shall make exactly n selections? Okay. So we have an urn. In this I have 4 white balls and 4 black balls. Every time I choose 4 balls, right? It's possible all 4 are white. It's possible I can get any combination, right? I can get 1, 3, 2, 2 and everything. So what I do is Here, if I get two white and two black, I stop selecting. Anything else, I replace them, right? I keep them back. Whatever I drew in the previous this one, balls, I replace them back in the urn, replace in urn, and select again. So this is like a loop sort of a thing. I keep on selecting and I wait until I get this one, right? So yeah, so this is the question, and so the question is basically, what is the probability that I will make n selections? Okay. So any thoughts how we should proceed here? Any ideas?
I have one question. So, is it instructions which we will be getting from looping itself, or is it like excluding the two whites and the two blacks?
Sorry, you saying that?
I'm saying that in your last line it is written we shall make exactly n selections. So, is it like n selections including the two whites and two blacks, or is it excluding?
No, it's including.
It's including, right?
Yeah.
So can we do it in this way, like n minus 1 selections would be like those which we are looping, and 1 which is like 2 and 2 whites and 2 blacks. So
Right.
n minus 1 would be like that loop which we saw over here, like other connection, and 2 whites and 2 black will be one connection. So total can create into n collections. Can we do it in that way?
Right. Okay. So what we are looking at is something like this. So I can say that my n selections event, I can break this down into n minus 1 selections of not two black and two white, right? And then I can say followed
1,
by
2 and white,
one
2
final
black.
selection, right? Which is basically which has two black and two white. Okay. Yeah. Okay. How do I proceed from here?
2.
Any ideas? Okay. So first thing we'll need to assume some certain things here. It's not given, but we will say that we'll assume that all selections are independent. Independent events, right? Now we'll see why this assumption is required later on. So the right now we'll use something it's always best to have some sort of a notation to work with. So I will give a notation to stopping event, which is saying that I draw two black and two white balls, right? And S bar is anything not S, right? In some sense, you draw anything else is something that I'm not interested in, right? So the probability of the probability of doing n selections can then be broken down into saying that I want to look at the events which are of this format, right? S bar, S bar, S bar, S bar, n minus 1 times, right? They should always come n minus 1 times, right? or should always be not S and then followed by a single S. Does this make sense?
Yes, yes.
Right. So this is from basically the definition of how we have defined n selections and how we have understood the question and how we have defined your events S and S bar. Okay. Now the thing is, this assumption that we made that all selections are independent allows us to break it down like this: probability of S bar, probability of S bar, probability of S bar. How many times? N minus 1 times into probability of S. Correct? And why is this? This is because of the independence assumption. Yeah. Somebody had their hand raised. Okay, fine. Independence assumption, right? Because we know that the probability of AB is probability of A into probability of B if A and B are independent. Fine. Now, continuing on the problem. So this is just multiplying the same thing n minus 1 times. So I can write this as probability of S bar power n minus 1 into probability of S, right? Now, what is the probability of S? Anyone want to take a dig here? What's the probability of S in this case?
Can I try?
Yeah, sure, go ahead.
So we have around, I guess, 4 black balls and 4 white balls, right?
Right.
So it would be like, considering 2 black balls would be like 4C2 into 4C2 for the white balls, 2 white balls divided by total number of balls, which is 8C4. This, like, I think so.
This is right. This one, right?
True.
Okay.
Yeah.
Okay. Anyone has any issues with this? Shall we go ahead with this? Is this right? No. Yes.
Yes.
That's right. Okay. Cool. So, what does this come down to? This will be 6 into 6, and this will be 8C4. So, I think 8, 7, 6, 5. Right. So 2, 3, yeah. So it will be 18 by 35. And this is probability of S. Now what's probability of S bar?
1 minus of 18 by 35.
Right. Is it 17 by 35?
Yes.
Yeah.
Right. That's it. This is the answer. So 17 by 35 power n minus 1 into 18 by 35. Alright. Simple. So does this formula remind you of something? What does it seem like? Which distribution does it remind you of?
Geometric.
Right.
8C4 is 35. Can you revise it once again?
No, 8C4 I think is 70. I just put it here.
Okay.
Solved it here. Yeah. So this reminds you of geometric distribution. So if I had to, pose it as a geometric distribution problem, what are we basically trying to do, right? We have events S and S bar, right? And we're asking I'll keep on doing my experiment. I can get either S bar or S, obviously. One of these two will come. And I'm saying, what is the probability that S comes the nth time? Right? This is what we are saying. Or you can say that what is the probability that the first time S comes is the nth trial, right? Or this basically saying what is the probability of first success in some sense. If I say that S is a success event and S bar is a failure event, you're asking probability of first success, right? This is basically how your geometric distribution goes by, right? Okay, so this is the so this is one problem that I had in mind. Then second thing, I'm assuming you guys went through Numpy tutorial, right, on Tuesday. So therefore now what we'll do is we'll just go through how we can do linear regression using Numpy. Okay. Okay. Does anyone remember what is the final equation we get for the weights in this problem of linear regression? Let's say if X is the set of features, right, which belongs to R power P, some P dimensional space, and Y is some variable that you want to regress over, real variable sort of thing, which belongs to obviously R, right? So if I had to do this, we are basically trying to solve a problem of this format, right? We're saying, can I plus B, and you put it like this, you say W prime X prime, where X prime belongs to R power P plus 1, right, where the first column is all ones, right? So if you have in this format, what is the let me just use this as X bar. I'll use this as X prime. Yeah. So what is the formula for getting these weights from X and Y?
It is X transpose X, the inverse times X transpose Y.
X transpose Y, right? Okay. So now we'll just look at an example data set and see how to do it in Numpy. It's kind of straightforward, but yeah, let's see just how to do it. Can you guys see the collab notebook?
Yes, sir, we can see it.
Okay. All right. So this is what we just discussed, the formula for the getting the weights from X and Y. So in Numpy, let's say if you have to do transpose, this is this one. So given X and Y, I'm first doing the transpose. I'm getting the X transpose, saving it in here, and I'm getting the inverse by multiplying these X transpose and X. That's the inverse that I have. I multiply that with X transpose, and then the whole thing I multiply with Y. Okay. This is the way you get the weights. And I think you also had a small introduction about sklearn today. So we'll see a sample data set here, something on diabetes, right? So if you see here, this load diabetes gives you diabetes X and Y. So X is all your features that you want to use to predict the variable Y, right? And Y is a real valued variable. So you can see here, shape of X is basically 442 comma 10. So what is 442? That's the number of samples you have in the data set, right? And 10 is the number of features that is present in the data set. And as expected, the number of rows, I mean these values that you have is also 442 here. Okay. So, and we can just look at how diabetes X looks like, right? So these are all your values, 10 values of each of these 442 samples, and diabetes Y is like this, right? So you have 442, and each of these has some measurement of the diabetes of the particular person, right? All right. So we'll try a univariate regression. So let's say I have one feature. I'll say I'll use a third feature in the data set to predict my y. So so third feature means I'll use all the samples, and I will take the x comma 2, right? So you can see here, these are all your variables in this particular column, right? And the shape is, as expected, 442, right? So see, when you index numpy in this format, what has happened is you'll get an array. The issue is we need it to be in a matrix format, right? So what we do is we say just reshape it. And so what -1 does is it says, okay, take whatever is there here and keep that dimension same, but make it into a cross one sort of a dimension, right? So if you see the shape now is 442 comma 1, right? Which is, so that's a matrix. You have 442 rows and only one column because you have only one feature you're trying to look at. And as we know that what we do is we add ones for all of these x that we have data set, right? So what we do is basically here, if you see, we're adding that ones to this particular x and making a new x, which is having 442 rows and 2 columns. So if I see here, what is x? So this is all so the first column is basically all just ones, and the second column are all your values which were there here, the actual x that is there, right? Okay. Now what I will do, I'll just run this get weights formula that I have, and simple. So the first thing would be what, basically? Any idea? What is the first weight here?
Intercept.
The intercept.
The bias term.
Bias term, right? So this is the bias term, and this is the particular weight for the particular feature that we used, right? So the third variable that we used, that is this particular the coefficient for that particular weight, right? Okay, simple and straightforward. Next, we'll go for multivariate. In multivariate, the idea is that I want to use all the data. That is, I have 10 variables. I want to use all the 10 variables. And I need to do once again this thing that, I have to add these NP ones, right? I need to add the ones for this particular shape. So if you see here, X is now a 11 dimensional this one, and each of these first entry will be 1, right? Indicating that we've added the ones in the beginning. And then we have, when I use this get weights matrix, I'll get this, right? So if you see here, so 152 is again your bias term, that is the intercept, and these are all your coefficients for each of the variables. So if you see here, w dot shape is going to be 11 dimensional vector, right? Because I have the first one being the bias and the remaining 10 being the remaining 10 being the coefficients for the remaining 10, the actual 10 variables that we have, right? Okay, and I think you guys discussed, right? In the class it was taught that it's possible that your X transpose X, okay, is non-invertible, right? We're trying to inverse a matrix. It may be non-invertible. So any ideas how we can solve in case it is non-invertible?
We use a
Sorry?
We use a ridge out there.
Ridge regression, yeah. So we can use a ridge regression. And what happens when we use ridge regression actually? How does it make sure that your matrix becomes invertible?
You'll be adding a factor called as lambda I, where lambda is any scalar and I is the identity matrix, and that will somehow, to make your matrix invertible, right? Even though it is non-invertible. So
Correct.
addition of that will help you, in getting invertibility.
Right. So when you do ridge regression, what happens is you have W x transpose x plus lambda I inverse x transpose y. This is what the weight looks like when you use a ridge regression with parameter lambda, right? So yeah, so this is the idea here. So how does it help? Any ideas why? So you said okay, adding it makes it makes it somehow invertible. Why that somehow, and what are the constraints on lambda? Can I use any lambda? Can lambda belong to real number line?
No, lambda is greater than 0.
Greater than 0, right? Okay, so lambda belongs to R plus. So why does it make it invertible? What is the idea here?
For any singular matrix, any of the two column vectors will be dependable.
Right.
That is, they will be in a linear combination. But if we add lambda, means that term will be breaked. It won't be linearly dependent. So
Right.
we are breaking it to lambda.
Right. So x transpose x, if it is singular, we see that yeah. So your columns are or whatever columns are linearly dependent. At least one column is dependent on any of the remaining, right? Okay. So if this is the case, so adding lambda I. So what is lambda I doing, right? So it's adding a factor of lambda to each of the columns, right? To each of the columns, but adding them at different places, right? So column 1 will get it in the initial place, column 2 will get it in the second place, and so on, right? So if there is any linear dependence, that will get broken down because of adding this lambda at each of the columns, adding it separately. We're not adding it to whole matrix together, right? It's not like I'm adding a factor of lambda for all the elements of the row of the matrix, right? So this causes the dependence to break, and therefore this finally becomes a invertible matrix. Okay, there are multiple views to understand this. This is one view. The second view of looking at it is basically, see, in the linear regression, you try to solve for this MSE error, right? The mean squared error, or squared error in some sense, actually. So you said I will look at each y w transpose x n, let's say n equal to 1 to capital N. This is your number, these are samples, and you're trying to look at this squared error. You're trying to minimize this squared error, right? This is what you're trying to do. So by adding this ridge regression sort of approach, so what's happening is you're saying I want to look at the error, not just the MSE, but plus some sort of a factor on the weights also, right? So you're saying that these weights cannot grow arbitrarily large because of this factor lambda. Okay, so when you do in this format and you do your whatever calculus and stuff like that, you will again get back, you'll basically get this form again. W will be equal to x transpose x plus lambda I inverse x transpose y. All right, this is one thing. So from this particular way of looking at it, so yeah, so that's one approach using ridge regression. Another is basically you can look at something called as pseudo inverses, right? So the issue is this one, right? I'm not able to invert this x transpose x. So there's something called as I think Penrose inverse, if I'm not wrong. Right, Penrose inverse. So that basically looks at x transpose x plus sort of a thing. The thing is different, and what you do here is you look at SVD of x and try to find out inverse from there. Okay, so SVD of x is, you will get that what is it called, U
Sigma V
V
transpose thing.
transpose sort of a thing, right? Now you will use this to get some sort of a inverse from here, to inverse for this. No, I haven't actually done this ever, but yeah, so this is another approach that you could take, right? All right, so here, let's say we have a non-invertible matrix. I'm just constructed it here. Yeah, non-invertible issues. For example, let's say I have this matrix which is of this format. I can obviously do all of this transpose, multiplication, and everything. The place where it fails is the inverse, right? So it says that it's singular matrix, so we cannot do the inverse here. So one solution, as we saw, is from bridge regression, right? Where now instead of doing just for the product, that was this, this x transpose x, I will add the lambda, that is L in this case 0.1, and the I matrix that is there, right? So np.I gives you the I matrix, and if I do this now, inverse starts existing, right? And you can play around with this lambda. You can make it like very small. You'll still get the inverses. Oh, I have to run this thing. Yeah. So you will still get these inverses. Okay. Any small positive number is sufficient. 0 obviously won't work. That doesn't make any sense. So any positive number will work to make sure that this is now becomes this particular product and sum becomes your invertible matrix, and then you can apply this formula for your this one. Yeah. All right. This is all I had for today. Any doubts you guys have about anything? Oh, by the way, I just want to remind you that that week 1 and week 2, if I'm not wrong, right? Both of these two are assignments are due by 10th August, which is this Wednesday, right? 10th August, 11:59 p.m. So make sure you submit them. Yeah. Okay. Any doubts?
Yeah, I have not doubt, but I have a question. Like the book PDF provided, its print was very poor. Some of the text are not being readable.
Okay.
And last video what you made on last Saturday,
Yeah.
that video is just stuck in between when you were explaining.
Yep.
We had these files where we can go, but that video was just stuck.
Correct.
So
Yes.
I don't know what to do with that, but yes, that is one.
Yeah, hence what I did was I mentioned it here that last time there was some issue with the videos. So I have basically right now what I'm doing is I'm actually live streaming to YouTube right now. So at least the reason why it didn't record properly might be because my laptop was not able to handle so much video. So hence I've done it streaming. So let's see. Hopefully it should work this time.
Yeah, thank you, sir. Thank you very much.
Yeah.
For your answers.
Okay. Anything else? Any other doubts?
Yeah, the book provided in that print, sir, if it can be looked into.
Okay. I'll do that. Yeah. So you're saying that the week 1 PDF is very poor quality, is it?
Yeah, actually there was a book of 700 pages, or I think more than that. That is some of the snaps are not being visible properly.
700 pages PDF. Which?
Yeah.
Whose?
Yeah, I got a PDF. Let me name it so that it will be helpful.
All right.
That is, I think, just the transcript of the whole lecture.
No, it's a kind of PDF. It is Introduction to Machine Learning, and by Professor Balram Ravindra.
Yeah.
It's a transcript of the video.
It's a transcript. It is saved in a PDF format in a running.
Yeah, that is helpful. That is very, very helpful. That's why I was pointing. But some of the snaps there I can say. The material is good.
They were very poorly taken. Actually,
some of the snaps are not good. Yeah.
Okay.
Yeah, resolution snaps. Yeah.
Okay. Fine. Okay. I'll talk to sir and the other TAs of this course. Okay, to make sure that we get a better transcript PDF, right?
Yeah, that will be helpful, sir. Really helpful.
Sure. Yeah. Okay. We'll do that. All right. We have any doubts here?
Hi, Raj.
Yeah. Who is this?
I just
Yeah.
had a question. You compared two methods of taking inverses. One was a pseudo inverse, one was the ridge regression.
Right.
So, are there any differences in the final outcome, numerical outcome of the two processes?
Yes, there will be. Because I think the
Yes,
way,
that's what I was thinking.
yeah, because the way your, your this one pseudo inverse works is basically you're trying to find some sort of
A smaller subspace,
yeah, smaller
invertible
subspace
subspace of the whole matrix,
where
right?
where you can get the inverse. Whereas here, and you can see actually
Regularizer.
in using so basically using a different lambda, you're getting a different inverse matrix itself, right? So each
Yes,
lambda is going to
yes.
give you a different w as such, right? And choosing lambda and then becomes sort of like a way to look at how MSE is changing, all of that. So
Yes.
you can't actually have a you don't have any way to choose a lambda mathematically as such. You do it like you choose which has a best least
Validation.
MSC and stuff like
That,
that
from the validation set, say.
from the validation set. Correct.
But that's what means the ridge regression is statistically much more well grounded rather than the pseudo inverse in this case. Shall I put it like that?
Uh, no. See, pseudo inverse is also properly, well grounded. No, you have like you have you using your SVD and trying to make sure things are working
Yes.
fine there. So I think both are good enough. It's just that the approach to the problem is different. Yeah.
Okay. Okay.
Hello, good evening, sir.
Yeah.
Sir, I'm in first year, and taking this course is fruitful for me or not? I don't even know Python. I only know C++ and C language.
Okay. See, these Python exercises that we are doing is basically to augment your coursework that is going on. So in case, for example, let's say tomorrow you want to understand how can I visualize things, it'll help
Yes.
you in that sense. So not knowing Python doesn't affect your course understanding for this particular course at least. So I'd say go ahead and attend the course. It's just that you need to put some effort to understand the math behind it, but I think all of that is well taught by sir in the lectures, right?
Okay, sir. Thank you, sir.
So there was one question by Khaja Ahmed. How to select root based on attributes in a decision tree? All right. Okay. Before that, what is all the binomial? No. Yeah. So it's a geometric distribution. Yes. We will share the IPNB file also. So what will happen is the week 2 the folder that is present, I will upload both the week 2 PDF and the IPNB file, the collab file. Okay, fine. Coming to this question of how to select root. So this is for decision trees, right? So ideally, so what you will do, see, choosing root, okay, is basically just choosing the best feature at that particular point, right, where you have no other knowledge of which feature is the best. So what you will do is you'll basically just iterate over all features. Okay, iterate the features, and each of the feature you will find what is the best gain or whatever. I think so there are two measures if I'm not wrong. One is the gain, I forget the exact name here, gain and entropy, right? So which gives you the highest, sorry,
Gini is one name and entropy
Yeah,
is another.
Gini index.
Gini index, right? Correct.
Gini index.
Gini index.
Yeah, right. Gini index, correct. So Gini index, so which gives you the which based on whatever you want to use measure, you will choose one measure and you will choose like whichever gives you the highest gain or highest highest entropy difference. You will use that to choose your best feature. Okay, that's the way to do it, Khaja. If you have any other, you want some more clarification, we can discuss more.
I think you should wait for those classes comes, and it should go in a I mean ascending order. I mean one by one things you should learn. I mean this is very first start. We have to study in a decision tree, and then in there it will come.
Right. Yeah. So we'll come to the decision trees. I guess in week 4 or 5 or something, and then we can have a discussion. Yeah. Is it possible to share the previous videos? Yeah. Isn't it shared, Ratnam? And you mean the previous video in the sense the previous live session video? I think that is already shared. If it's not, I'll confirm with the NPTEL team once again.
Raj, I have one question with respect to feature selection, right? There
Yeah.
are many methods, forward, stepwise, forward, stage-wise, backward, subset selection.
Yeah.
According to your experience, right, there is no one solution, that can tell you, right? So according to your experience, which is your favorite method of, selecting variables?
My favorite, I would say, is forward. Like you start with one feature, keep on adding and stuff like that. That is what I like to do, because then you understand exactly which sort of gives you the best sort of an increase. But as you said, like there is no one way to do this. This is just I mean, yeah, we don't have a clear solution. At least I don't have.
Yeah.
Yeah. So and as far as I know, like there is no sure short way of like this is the best way to do it, or this will give you the best result every time. There's nothing
Yes,
like that.
yes. Yeah, thanks, Raj.
Yeah, just to add on, forward selection should be greedy, right? So there should be some downsides to it also in certain cases.
Right. Yes. Yes, that is true. Yes.
We are in probability class, I believe, right?
Sorry.
We are in probability class, right?
This is week 2 linear regression.
Linear regression.
Yeah. All right. Anything else? Any other doubts you have? Okay. So by the way, so from the next sessions, I'm thinking that we can have like one problem from either linear algebra and probability, and some of these Python sort of thing. So do you guys want only problems, or do you want only Python stuff like that? Is any opinion?
I think it's better if we have a balance of both, right? So that we get hands-on, solving problems of linear algebra and a hands-on experience of working on Colab and things like that.
Okay. Good.
And also, Raj, will it be possible to supplement the classes with some real world data sets so that we can get a handle on how it is done in practice?
Okay. Yeah. Sure.
That would be very beneficial.
Yeah.
Yes. Agree to your point.
Yeah. So I work in neuroscience, so I should probably be able to get some brain data, and there's the one who does it previous to this, Kaushiki, works on some satellite data, I guess. No, not satellite. Yeah, so she can get some real world data from there also. So we can do that, not a problem. Yeah.
So brain data means, I was just curious, is it fMRI data or something of that sort?
Yes. So I work on fMRI generally. I've been working on fMRI for a while now. Yeah.
Okay. And Kaushiki probably remote sensing or something of that sort, probably. I'm not sure.
I think so, yeah. I forget, but yeah, that's what it seems like.
Yeah, that would be very great if you could supplement with your day-to-day data set so that you could give your own personal insights to those.
Got it. Yeah. All right. Sure.
Yeah. Thanks.
This is my first class. How did I get previous videos and assignments questions of week 1 and week 2? I think it should be all on the website, Sai. If not, I would say mention in the discussion group that you'll get people. I mean, you'll get links there. Yeah. All right. Anything else? Okay, if nothing else, I think we can close for now. Yeah, so next class we'll do again similar for sort of a approach. We'll have one problem, from either linear algebra or probability, and we'll do something on Python. So based on whatever course content is completed, we'll look at one of those things. All right. Okay. See you guys and all the best.
Yeah, thank you, Raj.
Thank
Have a
you.
nice
Thanks,
evening.
sir.